B.3, explanations for quiz 2 questions, number 5 and number 6. So number 5, here there is a basic concept I need to explain. An efficient algorithm, here we're talking about some algorithm, relatively efficient, does not have to perform well for the relatively small problem size. Some students may get confused. I noticed several students, so when they look at this question, so they did based on their intuition. So they thought an efficient algorithm has to do well for all problem sizes. So not necessary. So here the answer does not. The answer is true. Let me explain. There are several points I need to explain here. First, an algorithm is efficient or not. An algorithm is efficient or not. We look at the long run, not short term, long run. It is a long run behavior. All right? Why is that? Let me explain that. The typical in a computer program, when we implement it, writing a program, we need to do a lot of preparation, right? To write a program. So we need to do a lot of preparation. All right, the setup, right? Data structure, resources arrangement, right? Get things organized. So we need to do a lot of setup. 1, 2, 3, 4, 5, a list of useful things. We need to do that. This kind of preparation, we call it overhead, the overhead part. The overhead part, we need to pay, because we need to use resource, we need to use time. So that is the cost we need to pay for the overhead part. All right? Now, based on this, knowledge, this knowledge, now let's look at the problem with a relatively small problem size. All right, so now we want to solve the problem size relatively small So let's look at the situation. Let me draw a diagram. Suppose this circle represents the total execution time we need to use solving this problem. So this, the problem size given here. All right. When you do it, you need to pay this much for the overhead. All right, Then the remaining part, now that is the part you really spend on your problem. Okay, really do the computation. So that's the preparation. This is the, real computation. How about that? Real computation. That part, all right, when the problem size is small, all right? Yeah. Then let's go to the large problem sizes. Yeah. So you can imagine some pretty big problem size. This time we work on the same problem. Yeah. This time, let me use a large problem size instance. Yeah, so one special instance. Yeah, the space limited, but I still need to draw this circle represent all the execution time we need to spend. Yeah, but this time the preparation, the overhead part, preparation part, pretty much relatively stable. Yeah. So when you need to work on large problem size, your setup part, your resource arrangement part, pretty much close to when you work for relatively small problem size. Maybe a little more, slightly more, but not significantly more, slightly more, right? So, but as the percentage, this portion. All right, then the remaining, most of the execution time, remaining part, that's for the real computation part. Real computation part. And when the size becomes larger and larger, the percentage, if we look at the percentage of these two parts, overhead part becomes smaller and smaller in percent. The real computation part becomes bigger and bigger. All right. So we can use, some concrete number, 1%, less than 1% for the overhead part, and more than 99% for the real computation part. Now you can understand an efficient algorithm does not have to do well for the problem of smaller sizes. The reason is you need to factor in the overhead part. The overhead part may occupy large chunk of the execution time. So the overall execution may not be that fast because the overhead part makes the distortion. But when you look at the problem size very large, that portion so little, less than 1%, so little, so you can ignore it. You can ignore it. You just focus on the real computation part, and it is efficient algorithm. It's supposed to do well for that part, for real computation part. All right. So that is the background of this question. Here, let me connect to another important terminology in our wording, the definition when we talk about asymptotic notation. So if we want to study the concept, we need to go back to the asymptotic notation. All right. Here I do not go through all the asymptotic notation. Here I only want to point out one special terminology we used in our definitions of asymptotic notations: sufficiently large. Did you notice that? We use that, sufficiently large. Sufficiently large. Do you have a question? How big is the sufficiently large? Right? Do you have any idea how much means sufficiently large? There is no fixed answer. There is no. fixed answer. Here you can call another situation, this terminology is quite subjective, not objective, because it depends on the given problem. It depends on the given problem. Yeah. For example, so here, in order to talk about this concept relates to the given problem. Yeah. All right. So, for example, for prob 1, 10 is sufficiently large. Okay, here. But for problem number 2, even 1 million, 10 to the 6th, 1 million is not sufficiently large. That's all possible. Yeah. So it depends on the given problem. Yeah. Why we use this sufficiently large concept? Right? Because we want to skip the overhead part. We want to skip the overhead part. We don't want to look at the overhead part. After we skip the overhead part, then we reach the part that we can handle using our formulas in a comfortable way. So here, I just explain in this way. After we skip the overhead part, then the remaining part, because it is dominated by the real computation part. So we can deal with it using our efficiency formula. All right, so that is the background for this question. Yeah. All right, the next question. Yeah, this one's pretty easy. Yeah, so I do not need much time. I can explain it quickly. Yeah. First, answer is this, n squared. Yeah, n squared. Yeah. But if you go back to the bubble sort, the procedure, so how do we run the bubble sort? Yeah. You can easily calculate the number of comparisons. Yeah. Here, the number of comparisons. Yeah. Here we count the number of comparisons, not the number of swaps. Because this number, when you count number of comparisons, that's the basic operations. We have this concept, basic operations, right? Yeah. It is stable. Yeah. It is stable. So for any input case, the number of comparisons, stable. Not like swap operations, not stable. For some input cases, the number of swaps very small, very low. For some of the input cases, the number of swaps very big. Yeah. Not stable, yeah. But this number is stable. Yeah. So how to calculate? The first round, you go through the array, whole array, you get n minus 1 comparison. Second round, n minus 2 comparisons, and so on. Yeah. The last one, you get 1. Yeah. So you add up all these numbers by the arithmetic series formula. Yeah. So n minus 1. Yeah. Is this formula belongs to big O or big theta? Yeah. More precisely, we use the asymptotic notation, big theta notation, n squared. Dominant term, 1/2 n squared. But when we consider the growth function, we ignore the leading coefficient. It's big, small, We don't need that part. Yeah. We only look at the n power of n part. Power of n part. Yeah. All right. Yeah. So that is question number 6. Yeah. So, and we finish our video B.3.